Good morning. I am Dr. Himamaheswara Rao, Assistant Professor of Physics, Department of Freshman Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Welcome to the lecture series Atomic and Molecular Spectroscopy. Today we are going to discuss vector atom model, electronic structure of the atom. So in order to evaluate the structure of atom, vector atom model is developed by using different ideas of Bohr, Sommerfeld, and many scientists. So the major applications of vector atom model are the electronic structure of atoms, the Zeeman effect, anomalous Zeeman effect, and Stark effect. These four are important applications of vector atom model. The vector atom model uses the central features such as space quantization and electron spin quantization. These two are very important, and these two quantization techniques are analyzed by using vector analysis. Let us see the electronic structure of atom, the first application of the vector atom model. So in this, in order to design the principal quantum number n, let us discuss about the principal quantum number n. So in general, an atom cannot be said to have a definite size. In general, if there is a nucleus at the center of the atom, electrons revolve around the nucleus in different orbits, either it is circular orbit or elliptical orbit. But these orbits are the electrons revolve around the different orbits, and again these electrons should be said as electron cloud. It is not rigid. The condition of arrangement of electrons are not rigid. So in general, it is said as electron cloud. It is not rigid. So we cannot say the atom has a definite size, but from a practical point of view, a definite size is attributed to the atom. So in that way, hydrogen atom is supposed to have a diameter about 1 angstrom. Hydrogen atom diameter is assumed to be having 1 angstrom. So if it is the nucleus, the size of atom, hydrogen atom, 1 angstrom from the center of the atom to the outermost orbital of the atom. So the electrons in an atom occupy energy or orbitals characterized by the quantum number such as n, principal quantum number, n, orbital quantum number, n, l, and azimuthal quantum number ml, and also spin magnetic quantum number ms. So these set of numbers defines the state of the electron. So if you want to describe state of electron, these quantum numbers are required. What are those? Principal quantum number, orbital quantum number, azimuthal quantum number, spin magnetic quantum number. These four quantum numbers combinedly defines the state of the electron. Okay, so the states in general, if we are saying the state of the electron means it is about the orbitals. So these are organized into subshells and shells inside the atom. Subshells and shells inside the atom. The possible orbitals corresponding to particular value of n are said to constitute a cell. So in general, if there is a nucleus, there could be several orbitals around the nucleus, and these orbitals are assigned with principal quantum number from n equal to 1 to n equal to 2, n equal to 3, like that, maybe up to infinity. So based on principal quantum number, we can define the size of the atom also. So all the electrons in an atom which have the same principal quantum number and belong to the same electron shell. So if there are particular number of electrons, if two or more electrons belong to same principal quantum number is same for two electrons. That means two electrons are uh, uh, staying in the same shell, belongs to the same shell. For example, this cell. Let us go to the next slide. So if the electrons having n equal to 1, principal quantum number n equal to 1 for particular electron, then it is assigned it with a shell, K shell of the atom. And electrons in the n equal to 2 state from the L shell, and so on. All the electrons that belong to n equal to 1 state from the K shell, enter K shell of the atom. And if the electrons having value, principal quantum number value n equal to 2 forms the L shell, and if the electrons having the n equal to 3, principal quantum number value n equal to 3, then it forms M shell. That way we can designate all the shells. Okay, for example, here principal quantum number or shell principal quantum number n, we are giving here n, and it is the designation of shell designation will be given like this. So if n equal to 1, the designation will be given as K, and if n equal to 2, the designation is L, and if the n equal to 3 for an electron, that electron will be in the shell M, like this. If n equal to 4, N, n equal to 5, O, n equal to 6, P, etc. So all the designations are given like this. That means here, if it is the nucleus, n equal to 1, n equal to 2, n equal to 3, n equal to 4. So this is the K shell, L, M, N shell. So this is about the principal quantum number. So here n equal to 1 for K shell, n equal to 2, n equal to 3, n equal to 4. We are drawing only circular orbits here, but it could be elliptical orbits also. We will discuss how these principal quantum number could be assigned along with the orbital uh, elliptical orbits also. So a shell, accommodation of electrons in a shell. Let us see accommodation, how electrons are accommodated into individual shells. So a shell characterized by the principal quantum number n accommodates maximum 2n square electrons. 2n square electrons. If n equal to 1, the first orbit n equal to 1 k, that means k shell, the maximum number of electrons can be accommodated up to 2. 2 electrons can be accommodated in the K shell, because 2 into 1 square equal to 2. And here for n equal to 2, n equal to 2, 2n square, the total or maximum uh, electrons that can be filled in particular uh, orbit having principal quantum number n is given by 2n square. So 2 into first orbit, total number 2 electrons. And if it is second orbit, L shell, the total or maximum electrons that can be filled equal to 2 into 2 square. That means 8 electrons can be filled in the second orbit. And the third orbit, 3 square, 18. 18 electrons can be filled in the M shell. And fourth orbit, that means N shell, 4 square, 16 into 2, that means 32 electrons can be filled here in this orbit. And so in this way, we can define the maximum number of electrons that can be filled in a particular orbit having a principal quantum number n. So we will find out the maximum capacity of electrons in the next lecture also. So here the value of n increases as the distance of cell from the nucleus increases. So starting first orbit, for a first orbit n equal to 1, as the second orbit n equal to 2, this is KL, and the third m n equal to 3. That means as the distance increases from the nucleus, the principal quantum number also increases. Principal quantum, that means if we go far away from the nucleus, that means the orbital number increases. That means the principal quantum number also increases. So the number of electrons that a shell can accommodate increases in accordance with the value of n. So as we go away from the nucleus, the filling of electrons also increases, because as the number increases, n value increases, principal quantum number value n increases, the number of electrons filling in that particular principal quantum number also increases. Okay, so thus a K shell with n equal to 1 can be filled up to 2 electrons. L shell with n equal to 10, L shell means the principal quantum number n is 2, so it can accommodate up to 8 electrons, and so on, as we explained in this diagram. So these are the numbers for this is K shell, K, L, M, N. So in this way, we can calculate number of maximum number of electrons that can be filled in a particular orbital. So let us see about subshells. There are subshells also along with the shells. For each shell, we can accommodate subshells, individual subshells. So cells are built from subshells which accommodate electrons of the same value of the orbital quantum number L. So, subshells are the shells within the main shells, which are having the quantum number, orbital quantum number, same quantum number. All the electrons with same quantum number will be accommodated in the subshells of same cell. So thus electrons that share a certain value of L in a shell said to occupy the same subshell. If L value is same for electrons, those electrons are filled in the subshells of the same shell of single principal quantum number value. So the number of subshells in a shell is equal to the value of n. In general, if for example K shell, for K shell, the principal quantum number is 1. So the subshells in this shell will be 1. The total number of subshell for n equal to 1, we can have a subshell that is L equal to 0. That means 1 subshell is there. An L shell has 2 subshells. For L shell, that means n equal to 2, the L values are 0 and 1. That means L values are 0 to up to n minus 1. So if n equal to 2, we can find two subcells having values L equal to 0 and L equal to 1. If for the shell m n equal to 3, that means we can find three shells that are having values 0, L equal to 0, 1, 2, three subshells. For n equal to 4, that means we can find subshells having L values 0, 1, 2, 3, 4 subshells. So the subshells in a shell is equal to in a particular shell having principal quantum number n will be equal to n only. So there are n number of subshells in a particular orbiter having principal quantum number n. So according to atomic physics, states with particular value of L are designed with particular name. So for example, a state with L equal to 0 is called a state. If L equal to 1, those electrons belong to the p state, and etc. So if L is equal to 0, L value, let us draw the table state. Here the second row is the state. For L equal to 0, it is assigned with a state. If L equal to 1, P, L equal to 2, D, L equal to 3, F, L equal to 4, G, L equal to 5, H, 6, I. So in this way, the subshells are assigned with the individual states S, B, D, F, G, H, I for 0, 1, 2, 3, 4, 5, 6 values, etc. We can define like this. So for a given set of values of n, L, let us see azimuthal quantum numbers. So for a given set of values of n, L and nl, there are 2l plus 1 possible azimuthal quantum numbers ml. So in order to find the total azimuthal quantum numbers, we need L values. Based on the L, we can say there are 2l plus 1 ml values. So it means that for a given value of nl, there are 2l plus 1 orbitals or electron states. In general, these ml values defines the orientation of our electron orbits. In general, we can say electrons are revolving around the elliptical orbit around the nucleus. So these elliptical orbit can have different orientations depending on the ml values. So thus, if L equal to 0, there is only one electron state. If L equal to 0, so if you substitute the L value in this TL plus 1, we will get only one electron state, 2 into 0 plus 1. So that equal to 1 electron state. If L equal to 1, 3 electron states are possible. So the electronic states correspond to the different orientations of the orbitals. So around the nucleus, electron can orient in 3 different directions for the case L equal to 1. So quantum state of electron, an energy state described by 3 quantum numbers. Those are n, L and ml. So based on these values, an electron occupies a single state, and these can be also 2 different spin directions. There could be 2 different opposite spin directions. So here ms is also included for the quantum state. So if we want to describe about the electron, we need 4 quantum numbers: principal quantum number, orbital quantum number, azimuthal quantum number, and spin magnetic quantum number. These 4 values defines the quantum state of the electron. So this is known as this particularly this principle. Even all these three values are same, but for two electrons, those two electrons will be having opposite spin directions. This principle is called Paul's exclusion principle, as we have discussed in the earlier lecture. So this principle indicates why electrons don't crowd into the lowest energy state. Generally, in the lowest energy state can be filled. Maybe we can fill more number of electrons in the low energy state, but it is not possible. So this principle, Paul's exclusion principle, restricts the crowding of electrons in the low energy states. So the electron spin is characterized by quantum number ms. So including these spin magnetic quantum number, there are four states which defines the quantum state of the electron. So thus each energy state consists of two quantum states. So generally based on these three quantum numbers, energy values are discrete. So energy of electrons can be defined based on these three values, but two electrons with the opposite spin directions can have same energy values. So there are two electrons having same energy values, but states are different. So quantum states of the two electrons are different for those two electrons which are having opposite spin directions. Okay, so let us see the difference between energy level and energy state. So in general, these two terms are used often in the same meaning. In general, energy level and energy state are used for the same meaning, but those two terms are different. There should be no confusion between the two terms. Those two, generally, energy level indicates the energy value of the electron, but electronic state, as we said in the earlier slide, two electrons having opposite spin directions can have same energy values, but their quantum state is different. So quantum state, if we say quantum state, we will need to include the spin orientation of the electron also. So three quantum numbers n, l and ml can be same for two electrons, but fourth quantum number ms should be different. So including these four quantum numbers, we need to state about the quantum state of the electron. So an energy level is determined the value of the principal quantum number n, and such a level corresponds to n square electronic states. So for example, for n equal to 2, there are four different electronic states. So the energy of electron is mainly determined by the value of n, but to extent by the quantum numbers L, ml also. So based on the orientation of electronic orbits, we can define the energy of electrons. Okay, so these are the references more for more clarity. So thank you all.
Like, share and subscribe. Hit the bell icon for more updates.